Hello everyone, my name is Abdurrahman Boulahtour, and today I'm pleased to present our work titled Towards Software-Defined TSN Scheduling, which is an eBPF approach for stream processing and delay analysis in the context of Industry 5.0. I will begin with the motivation behind deterministic industrial networks, then present the limitation in current TSN implementations. I will introduce our proposed software-defined solution using eBPF and walk you through the system architecture and its components, and finally show you the implementation details and a live demo setup. Industrial networks are evolving from field bus systems toward real-time Ethernet driven by the convergence of control, sensing, and diagnostic traffic. And this transformation is essential to meet the goals of Industry 4.0 and 5.0, including deterministic communication, protocol convergence, and ultra-low latency and reliability. Time-sensitive networking, or TSN, offers the tools to achieve these goals through standards such as IEEE 802.1 AS or QBV or CB that enable reliable and predictable Ethernet-based communication. However, TSN still faces limitation because current deployments typically map the CS or COS class of service fields to a small number of queues, which does not scale well to large number of streams. Also, all frames in class are often treated equally, which prevents fine-grained prioritizations. And traditional TSN standards uh, depend heavily on global clock synchronization to enable deterministic scheduling. While this works well in small-scale networks, it became problematic in larger or more dynamic environments because clock synchronization is hard to maintain and sensitive to topology changes and often requires precise hardware support. In contrast, IEEE 802.1 QCR introduces ATS, which operates asynchronously, and it assigns an eligibility time to each frame based on metric and eliminates the need for global time sync. So this makes the system more scalable and flexible for industrial deployment where precision time is not always guaranteed. And even though ATS provides flexibility, but integrating it into industrial system brings several challenges. Many industrial environments still depends on legacy protocols like Profinet or EtherCAT, which don't align with TSN's time-based mechanisms. And ATS also requires features like time stamping and shaping support at the hardware level. However, most PLC sensors and edge servers lacks native support for ATS, and even open source TSN implementations are either limited or tied to specific vendors. These hardware and compatibility constraints prevent widespread deployment of ATS today. To overcome these limitations, we propose a software-defined TSN architecture that uses eBPF in Linux. eBPF allows us to inject code into the Linux kernel data path, enabling real-time frame processing without modifying kernel source code. So this approach first allows us to maintain the performance while gaining flexibility, modularity, portability across Linux versions. And also it allows or enables the tight integration with SDN controllers. Our work makes the following key contributions. First, we implement or build a programmable eBPF data plan for ATS in Linux bridges. Second, we integrate SDN controller in our setup to provide the centralized management and stream level shaping coordination. Third, the entire metering, queuing, and scheduling pipeline is implemented in software, so no specialized hardware is required. Fourth, we use the eligibility time concept or parameter to prioritize streams even when they share the same queue. And finally, we conduct ATS delay analysis under realistic industrial traffic conditions. So here is an overview of the full architecture. eBPF programs run within Linux-based TSN bridges, and all shaping and scheduling mechanisms are based on ATS. An SDN controller here dynamically manages flow tables, rules, and policies, and also enables centralized control and coordination. On the left, we have the key TSN components, such as the TSN talkers and listener that generate and consume time-sensitive streams. TSN bridges shape, filter, and schedule streams using ATS. eBPF is placed at ingress or egress for stream classification, shaping, and queuing. And on the right here, we have the SDN functionalities or tasks for configures queue schedules and schedules via like the southbound API such as OpenFlows, and also including the flow tables management and policy enforcement and admission control and failure recovery. This is our implementation architecture. The setup includes all the TSN, asynchronous TSN components, the talkers, the listeners, and the TSN bridges. And also here we have an SDN controller. All of them are virtualized or running in as virtual machines on top of KVM on Linux. And these each two interfaces of this setup is configured or is configured in an isolated network, and all the bridging is happening here through the TSN bridge. The software that we are using here for switching is OVS, Open vSwitch, and here for SDN controller we are using ONOS. The communication between ONOS and the OVS or the TSN bridges is via the southbound API like OpenFlow, and the configuration of the controller is through the REST APIs. TSN talkers generate and send streams to the listener through the TSN bridges. And here eBPF programs are placed at these interfaces at either the ingress or the egress, depends on the functionality. So here we have the different the traffic types and the class definitions. So different classes map to specific priority queues with predefined payloads and rates, burst size, and these represent realistic industrial use cases like control commands, video streaming, firmware update, or logging. To conclude, we will present a live demonstration of the system in action. For more technical details and evaluation metrics, please refer to the full paper. The experimental environment consists of 4 virtual machines, one TSN talker device, one TSN listener device, a TSN switch or a bridge, and an SDN controller, in this case is ONOS. Then the TSN talker and the listener are connected through the TSN switch. And in an industrial environment, this TSN talker could be an PLC or a controller that generates streams such as start or stop signals, movement instructions, and this listener could be a robotic arm that will receive these signals or these streams and process them. And also here in the TSN switch, we are implementing the TSN ATS functionalities for handling the prioritization and the scheduling. And first, let's start by exploring the ONOS web UI. So as you can see here, this is a topology. We have our switch and the 2 devices connected. We have here the talker and this is the listener. And if we go to device section, our switch, we check the flow table. Here all the flow rules added to this device. And these are 2 rules that we just add them using REST API. So these to tell the switch how to forward streams that are going from the talker incoming interface to the listener, the outgoing interface that is connected to the listener. And also same time, so this is running on the user space and cannot be seen by the eBPF that is handling or is where the ATS algorithm is running. So that's why we have created a copy of this one in the switch kernel space for eBPF. So you can check that using this command, bbf tool map damp id, it's setting 6. Yeah, so this one is a copy of what of our flow rules added using REST. And what else? And for the node monitoring, we have used this tool, net data, which it's because since on nodes does not provide low-level metrics such as the net interfaces stats or like the queuing metrics. So that's why we are using this tool for getting this kind of information. And here, as you can see in the dashboard, so this is all the interfaces connected or available in our switch, including the internal bridges. And if we go to the quality of service section, so specifically at the Ethernet tree, which is the outgoing interface, the interface that is connected to the listener device. So here we can see we have for now just one class, which is the default class, and in a green color, and all of these are the background traffic are going through this interface or this class, sorry. And also, and before we start generating streams, it's better to check as well like the eBPF programs that are attached to that interface, and which is this one, this is the outgoing interface, and this is like the Ethernet one is the incoming interface that is connected to the talker. So if we to check the eBPF programs, we can just run this command eBPF tools prog list, and we can even grab sketch. Yes, we hear these are two programs are already loaded and are attached to the interfaces. So this is for incoming interface, this is for outgoing interface. And also we can display the eBPF map for the ATS algorithm parameters, configuration parameters, specifically the CER and the CBS for each stream. So to do so, we can just run this command. And here you can see all different streams and their CR and CBS configuration. This will be used to compute the eligibility time. And now let's start generating traffic. Specifically, we start by the XDT class, which represent a high priority stream in our setup. So we can use the iperf command or tool. So here we are generating these streams, different 4 streams in this same class. But before, we just need to enable the packet capturing here on the switch and also in the listener device. Okay, so now if we run the command, and here we can notice that we are capturing here some, like we are getting some streams and are well classified, because here we are detecting the priority of the stream or of the packet that belongs to which stream, and also here same thing at listener device. And if we go back to or return to the dashboard, net data dashboard, and here we can see that there is another now class is appearing, which is for the CDT class. And if we repeat the process, the same process, generating different frames of different streams for different classes, we will see also here we are capturing all of the frames, and same here also we are noticing that another class is appearing. And if we do the same thing for the third one, and same thing here for different streams, different computations for the eligibility time, and also here you see another class is appearing as well here. To analyze the results of this algorithm, we have used the frame we had captured in our earlier experiments. So as you can see here, this is the first experiment, and this aimed to address the challenge of multiplexing multiple streams within the same class, and also ensure that the high priority streams are scheduled and transmitted first. So here, for example, we generated huge or large number of frames, and also introduce some important delays. And as you can see, this is our important stream and as or the critical stream and has, of course, the lower eligibility time compared to others. So which, of course, guarantee that these frames of this stream will get scheduled and transmitted earlier than the other frames in of the other streams. And also in the second experiment, what we did, or we tried to optimize or adjust the ITS parameters, the CR and CBS parameters, to reduce the delay because here we had some important delay, and here with of course large number of frames, and here we tried also to reduce the frame count, and we were able to reduce the delay to have some values in order of milliseconds, one or like even up to 4 or 5 milliseconds. And also like the delay, the detail of these two experiments are in the paper. So if you have any additional questions or anything related to this, please don't hesitate to contact us. And thank you for watching.